I believe I mentioned in a prior video that I kind of think of chemistry in three parts. That we have atoms in the periodic table, that we have bonding, which is how atoms bond together, and then there are reactions and how different compound substances behave when they interact with one another. Atoms was chapter 4, bonding was chapter 6, and we're finally getting into reactions, which is what most people think of when they think chemistry. And you may be wondering, well, what are we going to do after this? Well, most of what we do is focusing on special cases of reactions. And so we're getting into kind of the final topic, but the big one that everyone thinks of when they think of chemistry. The other thing that you'll see here as well, though, is that we have quantities, and that's going to involve some math. We're going to go back to that dimensional analysis stuff that we hit earlier in the course, and it's going to come up a lot. And so that's where we're going to start here, section 1, the mole. Now, of course, you know mole as a animal probably, but mole is also a unit that we have in the metric system. And the English system actually uses the same unit, the mole. It's one of the places where we agree, just like we both measure time in seconds. But it is a number of items. It is like a dozen, or maybe a case, a gross, a ream, a bushel, I'm pretty sure is the same way as well. A score being 20 things. Those are all specific numbers. And although, yes, we tend to use ream with sheets of paper, and ream is 500, it could be 500 of anything. We use dozen, of course, with eggs, but you could have a dozen pencils, you could have a dozen shoes, or you could have a dozen pair of shoes. And it's the same kind of thing with chemistry here. We have a unit called mole. Now, the mole is a big number. Because atoms are so tiny, we have a mole, and that mole is 6.02 times 10 to the 23. So side note, I was taught 6.022. If you hear me rattle that off, just because I'm so used to saying it in the longer version, it's the same thing. If you want to use the extra digit on there, for me, you can. You may want to avoid that if you're doing homework online. It shouldn't cause significant rounding issues when it comes to sig figs, but it could cause your numerical answer to be slightly different, and it might count it wrong, unfortunately, if you're too precise. Anyway, 1 mole is 6.02 times 10 to the 23 things, pieces, items of whatever. And that is called Avogadro's number, named for Amedeo Avogadro, who had the idea of a mole, but he himself did not come up with this number. He actually worked with gases, and we'll get to the gas laws later on, and we'll have Avogadro's number there. But he imagined that if you had a container of gas, think of a balloon. Those are horribly shaped balloons. But if you have a balloon and the two volumes are the same, and one of them is, say, filled with air, and the other one is, say, filled with helium, that the amount of particles, the number of pieces inside each of them, are going to be the same. And it turns out that that is a reasonable assumption, because the atoms, the molecules that make up those things, are so tiny that you really do have an equal number of pieces. And so we can have moles of elements, and whenever we have a mole of an element, it is 6.02 times 10 to the 23 pieces, atoms, in this case, of that element. However, and I don't know why they didn't do a separate slide on this and just jump straight to the table here, but when you have 1 mole of water, it's 6.02 times 10 to the 23 molecules of water. And what that means is that there's actually 2 H's and an O, and so if we wanted to get to individual atoms, there's actually 3 times as many atoms of H2O. Vitamin C has a longer formula, and so it's there, and so then its mole of vitamin C is that many pieces of the molecule, that many molecules of vitamin C. For things that are ionically bonded, because that pattern repeats over and over and over again, we instead have the formula units, the simplest whole number ratio of pieces there. And so NaCl has 2 atoms over and over and over and over again. If we want to be picky, they're ions. But when we say we have a mole of that, it is 6.02 times 10 to the 23. Well, because of this, because we have 2 things that are equal, then we have 2 more conversion factors. We have inequality and conversion factors that we can use for doing calculations. And we'll use moles throughout this topic And so I want to point out one small thing, and that is when it comes to conversion factors, unless we have a conversion factor that is mole over mole, except for when we have mole over mole. If we have mole over or under anything else, the number that goes with mole is always 1 for now. It's just a shortcut to help you remember the conversion factor, because unfortunately we're getting into units that you're not familiar with. You're possibly not familiar with some of the metric units, but we're getting into things that are really strange here, Avogadro's number. The other thing I'll point out as well is frequently when I'm writing things out and showing my work, because writing out 6.02 times 10 to the 23 takes a lot of time, I will just write that out as A. Here we're given a problem. How many CO2 molecules are there in 0.5 moles of CO2? So you always start with what you're given, 0.5 moles. As a side note, we frequently abbreviate moles later on with the letter N. I don't know why that's chosen. M is already used for milli and a few other places, so that's my guess as to why M isn't used. I would assume that it is tied to number because we're using Avogadro's number. Mole is a stand-in for it, just like dozen is a stand-in for 12 or score is a stand-in for 20. Mole is a stand-in for 6.02 times 10 to the 23. Anyways, 0.5 moles of carbon dioxide. Keep your chemical units with you. Here in this chapter, we're going to get to chemical reactions. When we get to chemical reactions, it's absolutely essential that you have the chemical there as if it's part of your units. Anyway, here we know that we need moles in the denominator to cancel that out. We know that we can turn moles into particles, molecules, pieces, atoms. It just depends on what we're looking for. Here, in this case, it is particles. And we know that there are 6.02 times 10 to the 23. Didn't quite give myself enough room there. Particles of CO2 in 1 mole of CO2. And as I mentioned already, the number that goes with mole is always 1 if it's above or below something that is not moles. Moles cancels out with moles here, and so we're left with particles, which is what we're asked to solve for. How many molecules? If you wanted to call this molecules here instead, there's nothing wrong with that. Make sure, unfortunately, that you spell out molecules, because if you try to abbreviate it down to mole, then you have it. Oh, they didn't mention that, and I haven't yet either. Mole is abbreviated MOL, and I'll always do my L's cursive. I think I mentioned that, but it's not a great abbreviation. MO is molybdenum, one of the elements in the periodic table. ML is milliliters. ME isn't used elsewhere, but the E is silent, so I assume that's why. It's not a great abbreviation, but heck, we're going to use it often enough, dropping that E. It saves at least a little bit of time, I suppose, and that is the proper abbreviation for it. At this point, punch into a calculator, and we have 3.01 times 10 to the 23 molecules of CO2. I'm going to cut in a video clip here to show how to punch that into the calculator. I'm going to try to remind you of that E thing. For doing powers of 10, it's essential that you type it in that way when you're doing it in the calculator. The bigger thing I want to show you, though, is if you have a graphing calculator, if you have a non-graphing calculator, it depends on which brand you have as to whether you can actually store a number. But we're going to use Avogadro's number often enough that there's a way we can store it and have it save in the computer's memory so that we don't have to type it in over and over and over and over again. So I'm going to cut in a little clip here, show you how to do that. If you don't have the Texas Instruments graphing calculator, you don't have a graphing calculator, you'll need to do a quick search to see if you can find a way to do that with your calculator. And of course, you always can go the long route of typing it in, but I'll show you that shortcut and then we'll jump back to doing a couple more example problems. So that calculation we just did was 0.5 times Avogadro's number, 6.02. And then remember, to do powers of 10, it's second, comma, it says EE here in blue. It shows up as E on the screen, and that takes the place of times 10 raised to the. And so then we just need 2, 3, and there we get the answer we just had a moment ago. Well, like I said, we're going to be using Avogadro's number a lot, and there's actually a way that you can make your calculator remember that. Again, this is how you do it on pretty much any Texas Instruments calculator, although the specific layout is the 84 plus CE. It is very similar for all of the others. So start by typing in Avogadro's number, 6.02. Second comma to get that E, 2, 3. And then what we're going to do is we're going to hit this button right here above the on button. It says STO and has an arrow. On the screen it will display as just an arrow, but that stands for store. And so we're going to say store, and then we're going to just pick something for it. Now you have to change the cursor back to an alphabet one. So you're going to hit the alpha green button here, hit A, and that says that you're going to, your next input is an alphabet entry using the green letters that are above some of the numbers and buttons here, and we're going to pick A for Avogadro's number. If you wanted to pick N, because N is used to abbreviate moles frequently, you could do that. And of course you could do this with any other thing you want, and you hit enter and it doesn't look like it did anything. I mean, it looks like it just says 6.02 times 10 to the 23, and of course it does. But now anytime you hit alpha A, it remembers that A is 6.02 times 10 to the 23. So if we rerun this first calculation here, all I have to do is 0.5 times alpha A, enter, and notice it gives me the same answer here. Anytime you need Avogadro's number now, if you type just alpha A, it will remember that 6.02 times 10 to the 23. You could store whatever other variables you want to in there. There are some other ways that you can go about doing this and setting up equations for yourself even. Back in my day, we used to call these things not graphing calculators, but programmable calculators, because you could actually program on them. I got my start in computer programming by programming on a calculator, which does bring up one little clarification that I should mention. When you're doing coding, and you don't need to know about coding, but when you're doing coding, say you're doing a score in a game, well, let's say your score was 5, and in the program, if you earn a point in the game, then let's say that your score was stored as alpha S. So let's say that your score previously was 5 alpha S, and in the game, if you earn a point, then what you do is alpha S plus, let's say you earn just one more point, 1 store alpha S. And what that says is recall the score, which was 5, add 1 to it, and then right over top of that, erase it. And now you have that. And now when you hit alpha S, it's now 6. And so on. The reason I mention this is because if you do program on the calculator, you want to avoid using A as a variable. If you download some of the apps and games that are available for your calculators, then sometimes those will do the same thing in the background. So it never hurts before doing a homework assignment, before doing a test or whatever, to real quick hit alpha A and make sure that it hasn't been overwritten. If it has been overwritten, then you're going to have to go through there and store it again, or you can always go the long form way, just typing Avogadro's number in manually. But it's a quick shortcut if you're using a calculator like this. If you have a different calculator, you can do a search, can I save a variable or can I save a value, and look it up that way. Otherwise, you're going to have to type it. Just make sure that you use that second comma thing, the E, so that it treats this as a number instead of the multiply as a mathematical operation and follows order of operations correctly. Anyway, back to some more examples in the notes. On this one, we're asked to solve how many atoms are in 2 moles of aluminum. And so then we know that we need moles on the bottom, and we want atoms of aluminum on top. The number that goes with moles is always 1, and atoms is Avogadro's number, 6.02 times 10 to the 23. Like I mentioned, I'm going to abbreviate it, and you just saw how you can store it in your calculator and use A for that, and so you can even type it in there to your calculator as A. But when we do that, we're going to end up with 1.2 times 10 to the 24 atoms of aluminum, and that is C. Here we're asked to do the reverse process. We're given a number of atoms and asked to calculate the number of moles. So start with what you're given, 1.8 times 10 to the 24 atoms of sulfur. We know we then want atoms of sulfur in the denominator, and we're going to want moles of sulfur in the numerator. Number that goes with moles is 1. Number that goes with atoms is going to be Avogadro's number. And so then when we do that, we end up with 3.0 moles of sulfur, which is B. As I mentioned already, back on the table that had the mixture of atoms and formula units and molecules, the 1 mole of a substance has a different number of atoms in it, because again, mole is just a number like a dozen. But if we have each molecule of, say, aspirin here in this case, has 9 carbons, well, then that means we have 9 moles of carbon in there if we have 1 mole of aspirin. And it means that we have 8 moles of hydrogen and 4 moles of oxygen, which is what this slide here explains. It says that when you have these subscripts, or whatever subscripts in your formula, that 1 molecule then has that many pieces of each element. And if we have 1 mole of that molecule, then we have that many moles of that element. And so now we have more ratios that we can use here. More equalities means more ratios. What this means, though, is unlike in the past where we had, say, 1 inch is equal to 2.54 centimeters, we have just that one equality that became the pair of ratios where we have the numerator and denominators flipped. Now, every chemical formula gives us that many more, depending on how many elements are in there, that many more conversion factors that we can have. And so we now have a lot of conversion factors, and you just have to keep in mind that the formula gives you the number of pieces that are in there. In 1 molecule, if you have a mole or some fraction of a mole, as this calculation is going to have here, then we can get to number of individual atoms still. So this one here, we have 0.15 moles of aspirin, and we're asked how many atoms of O are in there. So that's just the oxygen. So start with what you're given, 0.15 moles of, I'm not going to use the formula there. I'm going to abbreviate aspirin ASP here. Well, we know that 1 mole of aspirin has 4 moles of oxygen in it. Now that 4 came from the subscript here, and notice we have moles over moles, and when we have moles over moles, the number is no longer just 1. But 1 mole of aspirin has 4 moles of oxygen. If we were just asked for moles of oxygen, we'd be done because those units cancel out. However, we're asked for atoms of oxygen, so we have one more step. We know that we can turn moles of oxygen into atoms of oxygen. And so then we want moles of oxygen here, and we want atoms of oxygen here. We could do Avogadro's number there, and we can do 1 there because the number that goes with moles is always 1 otherwise. And the moles of that cancel out, and we're left with atoms. So when we do that, we get 3.61. There's 3 sig figs here times 10 to the 23. Your power of 10, remember, is not part of the sig figs. Atoms of oxygen. Now, it turns out there's another way to solve this one, and I'm going to show you how to do that here. We could instead go to the amount of molecules of aspirin we have first. The way that I did it the first time was using the moles of the molecule and going to the moles of oxygen. The way I'm going to do it this time here is I'm going to use the moles of the molecule. I know that really doesn't show up, to get us to number of molecules and then get us to number of atoms. So this time I'm going to turn moles of aspirin into molecules. We know that there's a Avogadro's number worth of molecules in 1 mole of aspirin. And then we know that 1 molecule of aspirin has 4 atoms of oxygen in it. Then when we check our units, moles of aspirin cancels with moles of aspirin, molecules of aspirin cancels with molecules of aspirin, and we're left with atoms of oxygen. And we get 3.61 times 10 to the 23 atoms of oxygen still. And so it works out just the same, which is what we would expect. But I've mentioned before, this is what I absolutely love about dimensional analysis, is that we can work a problem multiple ways. And as long as we're careful to keep track of our units and make sure that our units cancel out the way that I did with slashing them through there, then we know we got the right answer. So you'll notice that we have 4, and we have Avogadro's number, and the numerator here, we have 1s in the denominator there, and of course we started with the same 0.15 on each of those. And so it's the same numbers that we end up multiplying by one another, but you'll note that the units that are with the oxygen are different in each of these. And that's okay, because as long as we're careful, keep track of our units, the units cancel out. We'll get to the correct answer. Anyway, you'll have plenty more practice over this, but that finishes section 1.